8 actually most often to verify that whether a space is a vector space. But 7 and 8 actually are crucial and critical for the linear property. Alright. And then theorem 1, it just means you times with the 0 in the vector space, you should finish with the 0 vector. Although reversely, you should also get the scalar times a 0 vector, so get itself. Okay. And the subspace definition actually helps you to know how to verify that whether a subset of a vector space is a subspace. So these 3 things are important actually. You need to ensure that 0 vector is still in that subset, and also it's closed under the vector additions and multiplication by scalars. So these 2 are linear properties of the vector space. All right. Okay, so the 4.2 actually about the non-space, column space, and linear transformation. So the non-space, to find a non-space, actually from the definition, you should know that you just need to solve the homogeneous system. So Ax equals to 0 and then find the x. So the x will consist of this non-space. And the column space is very direct. It's just a span by the column vector of a matrix. And row space is reverse meaning. You just get this span of these row vectors of the matrix. Right. So theorem 6 actually tells you that the row of the matrix A should equals to column space of A transpose, because when you transpose, the row vector just become the column vectors. Okay. And if it's a row equivalent, 2 matrices are row equivalent, and then the row space of these 2 matrices are the same. And also, if they are column equivalent, then the column space are the same. And the linear transformation, okay. So it's about the defined in the vector space. Right? And then given this linear transformation, we will have the kernel and the image. So its kernel is just like a non-space of the matrix. So you just find this transformation, but the pre-image of the 0 vector. So which means you find the V such that the transformation of such vectors V equals to 0 vector. All right. And the image of the T, you just do the like a mapping. So you just for some small V, and you find this W equals to TV. Okay, so the theorem 7 actually is important because it tells you that actually the relation with the 1-to-1 mapping and an onto mapping. So you will also have this test in the midterm. Okay, so we also call the 1-to-1 injective. So actually injective just is equivalent to the kernel. Injective kernel T equals to 0. Okay, 0 vector. And the surjective, which is the onto, just means the image T equals to the vector space of that transformation. Because the transformation is from the V to the W. So you just require the image T equals to W. Then it's onto. Actually, it's the clear in its name, onto. In the 1-to-1, actually, we all know that it should mean that homogeneous system just have a trivial solution, so we should actually correspond to kernel T equals to 0. Right. So these 2 things are the most important among here. Okay, let's check the example 1. All right, example 1 actually is a classical question for the to define a vector space, because it gives you some strange operations, but actually one is correspond to addition, one is correspond to scalar multiplication, and actually you want to know whether this set under such operations is a vector space. So, as I said, we usually made use of the 7 and 8. So we definition in the vector space, which are two linear properties. To get our idea first, that's whether it could be vector space. So it's just like use the same scalar or different scalar. So let's just verify under this setting in this example. All right. So okay, we still can choose the C and the D. So the scalar just change to the scalar multiplication in the setting. Okay, so actually we should know that this V is the connection of the order pairs. So which means that each element in this vector space should be a pair. So we use like X and Y. So actually by the definition of the such operations, we should get plus D times X and the Y. So on the left hand side, all right, so this is 8. So it's the C times the this and the D times this. So we just use the C scalar multiplication by this pair. And so we should make use of also that the addition, define addition. Okay, so all right, so actually you can get a bracket. Alright, so actually it's just a formal definition, and so we should get the result. Oh, this is a true one. Alright, so after this kind of computation, you will find a difference. It's happened as the second element of this pair. So which one of them is Y, one of them is a true one. So which just tells you that these two are not equal. So which just violates our this rule. Okay. So just contradicts one of the definitions. So which means the V is not a vector space. Okay, so actually we can also compute this property, but actually these operations are satisfied from this property. So which means sometimes you use these two. One of them might be true, one of them might incorrect. So you just spend a bit more time to find one. If these two are both satisfied, then it's quite likely that it should be a vector space under the operations. All right. So example 2 is to verify that whether a subset is a subspace of the big space or cubic. Okay. So first thing, we need to ensure that the zero vector is in this subspace. So which means actually under such a condition, let's say it consists of S and T, and both of S and T belongs to the real space. So we just can know the zero vector should be decided by making the S and T both equals to 0. Because S and T can be arbitrary number in the real space, so this is satisfy the definition. So which means the zero vector actually belongs to such a subset H. So this is the first rule. Okay. So we also need to verify the second and the third one. So if either of them is not correct, then it should not be a subspace. Okay. So it's closed on the addition and the scalar multiplication. So which means if we have for example, the vector U equals to S1 minus S1 and vector V. This 2. And then we assume that the vector U and the vector V belongs to H. So we just need to ensure that vector U plus vector V also belongs to H. So actually this is quite clear because you are doing the linear operation. So it's just combine the S1 with the S2 and the T1 with the T2. Actually, these are new S, these are new T, because they belongs to the real space. Okay, so it's obvious that the third one is also correct. So, which means if you have a vector U belongs to H, and you can also easily verify that CU belongs to H. Okay, so after this 3 verification, you can get the conclusion that the H is a subspace of R cubic. Okay, so this example is easy. Okay, but actually, for this kind of examples, you can just think more after solving it. So you can just, for example, think more. What is the real reason of this space is the subspace of R squared? R cubic, sorry. Can you think of the reason? Sorry? What's the real reason of the H is a subspace of the R cubic? So of course you can just follow these rules and you get the answer. But actually during this process, actually you can find some ideas. So for example, under our second verification, we should verify that the U plus V belongs to H. Actually, we make use of the S1 plus S2, T1 plus T2 is still belongs to R. So this is very important because only in this way actually is the correct under the definition. So which means actually the real reason is that we make use of the real space is a linear space. which means the real space is closed under such addition and scalar multiplication. So in that way, you can just get the answer that the G plus V still belongs to H. It's the S1 plus S2 and T1 plus T2. Similarly, the C times the S, they all belongs to the real space R. So which makes you satisfy the definition of the H. All right. Can you see that board?
That board? Yeah, sure.
Okay, thank you. All right, example 3 is just to we have a polynomial space, and we want to know whether a PT, so it's the 1 minus the t to the power of 4. All right, it's a linear combination of polynomials in another space. All right, and the space actually is spanned by the 1 plus t and such until the t cubic plus t to the power of 4. All right, so actually this is also direct. You want to know whether it's a linear combination, you just assume the coefficient, and then you just solve the equation. So as we should know that the same degree, the term of the same degree should have the same coefficient. So which means we just combine these terms with the same degree. So you just combine these two sides of the equation. You should get the answer is the C4 first equation equals to -1. So which means the C3 should equals to 1, because you need to cancel these t cubic terms and also t square terms does not exist. So C2 is -1. And furthermore, C1 should equals to 1. Also the constant is a C1. So if you can solve this equation, so which means you find such a coefficient, which means the PT is indeed a linear combination of such polynomials in X. So this kind of polynomials, they are all of the highest degree. It's different. So which means actually they can construct like a set of a base for this vector space. So which you just make use of this base and just times the coefficient before it and try to get in that linear combination. Okay, example 4. So we want to express the non-space of this matrix and the set of vectors. Okay, so to get a non-space, you just need to solve this linear system. So which is the matrix times the x equals to 0 vector, right? So because this is a very simple matrix, we can see. Okay, and also it's already in RREF form. So which means we can directly transform to a set of equations. So which you should be very familiar that actually this third column is a free column, so which means x3 should be a free column. So you just make use of this x3 as a free variable, sorry, to express the x1 and x2. So which gives you a general solution of this homogeneous system. x1, x2, and x3. Which is minus 2, t, and p. So it's p times the minus 2, 1, 1. Okay, so the non-space. Just express it as such a p times a vector. So which means actually this is a linear space and it's only spanned by this vector. So you can only do the scalar multiplication on it. So you always get a multiple of it. Alright. This is because of this system only has the one freedom. The rank is 2, but the image space is 3. Example 5, so which is also not hard to solve, because column space we know that is just column vectors of a matrix. So we want to find whether this vector V belongs to the column space is like solving a non-homogeneous system. So the most important actually is the first stage. It's just the write off the system you need to solve. So it should be in this way. You just make use of the column vectors of this matrix A. Alright. So normally actually you need to solve this non-homogeneous system. So it's just like this matrix and it finds the vector x. But for this question, it actually is really easy because the 1, 2, 3 is already equals to 1, 2, 3, which means the x1 equals to 1 is enough. And the other two gets the 0. So this is a solution of this non-homogeneous system. So which just tells you that the ratio belongs to the common space of A. Okay, let's check the exercise. Exercise 1. So exercise 1 is just we talk about a space of functions, so we can also call it a function space. So which means all of the elements of this space should be the functions. And actually, you want to know whether they have some like a linear relation. Yeah. So like this question, they want to know that whether tangent x should be a linear combination of sine x and cosine x. For this kind of linear combination question, we can just firstly assume that it is such a linear combination. So like C1 times the sine x and plus the C2 times the cosine x equals to tangent x. Okay, so which means that when x, we know that it's a function, but in the common domain, the domain is the 0 and the pi over 4. So So we can just make use of the common trick actually in our high school. You just get some special value of such x inside this domain to verify that whether there exists some solution. Because when you get the 2, like the special value, actually you only have the 2 unknown variable. So this system should have already have a solution. So when you get one more, actually you can see whether there is a contradiction. All right, so we get some special value because it involves the triangle mean value. So we get a 2 endpoint first, the 0 and the pi over 4. So that is the C2 and it equals to 0. So which gives you that the C2 equals to 0. And then on the other side, 1x equals to pi over 4. So we will get the square root 2 over 2. And make use of the C2 value we already get. So equals to 1. Tangent to pi over 4 is 1. So which just gives you the C1 should be equals to square root 2. Okay, so when we just check one more special value, so which of course should be the pi over 6 of this interval. So then you will get the square root of 2 as the C1 value and times the half. And then plus the 0, because the C2 is 0 and the tangent pi over 6, so it's the square root 3 over 3. So which obviously you get a contradiction. So the left hand side doesn't equals to right hand side. Okay, so just tells you that tangent x should not be a linear combination of the sine x and cosine. Actually, doing in this way, I think it's kind of based on the iteration at first. So firstly, actually, you should get the iteration of whether tangent x could possibly be the linear combination of sine x and cosine x. And actually, you can get the roughly the answer from the graph of sine x and cosine x. Because these two, you should be very familiar with their graphs. So they have a huge difference with the tangent x. So this is sine x and this is cosine x. But the tangent x is it's the other way. It's this way. This way, because it has a asymptotic line at pi over 2 and the minus pi over 2. So which means when you only do the linear combination, you can only like stretch or amplify the sine x shape and the cosine x shape. So based on these operations, actually you can never get the shape like the tangent x. Because actually it's a divergence of the pi over 2 and the minus pi over 2. But you can never do that with the linear combination. Because you always get finite values. All right. Okay, so exercise 2 and it's about non-space, and the exercise 3 is about column space. So actually they are all actually the computation of the linear system. All right. So you should, I think, you should take time to try it. How do you think? We just, I don't know. how about is the 36? How about we just try solve this question within 5 minutes, and I will check your answer. Like a training for your speed of solving.
great. It's great. But should add one more.
Yeah, it's x5. x3 and x5 are all right.
Yeah, I mean the 5-dimensional vector.
Yeah.
Yeah, but it's really quick. Let's go.
Thanks.
Not spaces, just the equivalent to solve the homogeneous system.